Module 2, Lecture A, Collections for Care. By the end of this lecture, you will be able to construct lists, tuples, sets, and dictionaries to represent common medical data items, retrieve, update, and organize patient-related values using indexing, keys, and built-in methods, and choose an appropriate built-in collection based on the structure of a medical task. Ordered medical readings. Patient data lists. A patient data list organizes medical observations when their order matters, such as repeated weights, pain scores, lab results, or oxygen levels. By keeping values in sequence, it helps clinicians and learners see trends over time and interpret whether a patient is improving or declining. Patient data lists can place related clinical entries in a meaningful order, even when the items are not numbers. They may show events such as medications, symptoms, procedures, mobility progress, or vaccine dates as they unfold over time. When building these lists, the order should have clinical meaning so it helps tell the patient's story clearly. When creating patient data lists, prioritize consistency, clarity, and ethical handling. Group only comparable values, such as readings taken in similar contexts, so the information can be interpreted accurately. Whether used in health records or mobile apps, these lists should organize sensitive patient information in a respectful and appropriate way. Python code patient data lists. Lists can store patient measurements in chronological order, so each value keeps its clinical meaning over time. Small examples help illustrate this while protecting sensitive patient details. A list is created to store morning glucose readings in the order they were taken. It contains 4 measurements: 118, 124, 121, and 116. Keeping them in sequence preserves their chronological meaning. Use the append method to add a new glucose reading to the end of the list. This keeps patient measurements in chronological order, with the newest value last, making it easier to track trends over time. Use the first glucose reading as the baseline and the last reading as the latest measurement. Comparing these two values shows how the patient's glucose level has changed over time. This line updates the second glucose reading in the list to 122. Directly changing that position corrects the recorded value and keeps the list accurate and up to date. Count the glucose readings to see how many measurements are available. Then compare the latest reading with the baseline reading to find the overall change in glucose level, which indicates the patient's trend over time. This line displays the glucose readings in the order they were recorded. Keeping the original sequence helps show changes and trends in the patient's glucose levels over time. The code prints the patient's first glucose reading as the baseline and the last reading as the latest measurement, both in milligrams per deciliter. This makes it easy to compare the initial and most recent values to see how the glucose level has changed over time. The code reports how much the latest glucose reading has changed from the baseline by subtracting the baseline value from the most recent measurement and showing the result in milligrams per deciliter. It also prints the total number of recorded readings, giving a quick view of both the glucose change and the amount of data collected. A list is used to store patient data because it preserves the order of measurements. Keeping this chronological sequence helps healthcare professionals track changes over time and supports accurate clinical analysis. This script shows how a list can store glucose readings in chronological order while allowing simple updates. It adds a new reading, retrieves the first and latest values, corrects one entry, and calculates both the total number of readings and the change from baseline. The output highlights that lists are useful for keeping ordered patient data and tracking changes over time. Tuple vital signs. Tuples are useful for storing fixed medical readings such as temperature, pulse, and blood pressure when their order matters. They keep related values together as one stable observation, which helps clinical data stay organized and consistent. This makes tuples a good fit for recording vital signs as a clear snapshot of a patient's condition. In medical settings, tuples are useful for grouping vital signs from one clinical moment in a fixed order that should not be accidentally changed. This matters because each reading is best understood in context with the others, not in isolation. By keeping values together, tuples help show a clearer clinical picture for assessment and communication. Tuples are best for data with a known fixed structure, such as a medical vital sign record, where each value has a set place and meaning. They make it clear which values belong together and should not change. If the number of readings needs to grow, a list may be better, but each fixed snapshot can still be stored as a tuple. Python code, tuple vital signs. Tuples are useful for storing fixed clinical snapshots, such as vital signs where the order of values matters. This example shows how to access tuple values safely by their position. A tuple can store a fixed snapshot of a patient's vital signs, such as temperature, pulse, breathing rate, blood pressure, and oxygen saturation. Because the tuple keeps values in a consistent order, each measurement can be interpreted accurately. A tuple is used to store the labels for each vital sign, such as temperature, pulse, breathing rate, blood pressure, and oxygen saturation. Keeping these labels in a fixed order makes sure they line up with the matching vital sign values, so each label can be paired with the correct measurement later. Set the expected tuple size to 6 vital sign readings. Then use the length function to check how many elements the vital signs tuple actually contains. This confirms whether the data has the expected structure before any further processing. First, print a summary of the vital signs tuple to review the stored clinical data. Then print the total number of readings to confirm the tuple has the expected number of elements before any further processing. Vital signs can be retrieved from a tuple by using their fixed positions. The first element gives the temperature in Celsius, the second gives the pulse rate, and the last gives the oxygen saturation percentage. Using these stable positions keeps each value tied to its intended meaning. This example shows that each position in a tuple has a fixed meaning. The first value represents temperature in Celsius. The second represents pulse rate, and the last represents oxygen saturation. Because the data is accessed by position, the tuple must keep a consistent order so each value is interpreted correctly. The label and value for each vital sign are paired using the zip function, which links the two collections item by item. These pairs are then stored as a tuple to keep the structure fixed. Printing the first labeled reading shows how the data becomes clearer and more meaningful when each value is matched with its label. First, check whether the vital signs tuple has the expected number of elements. If the count matches, the tuple structure is considered correct, and a true or false result is printed. This simple validation helps confirm the data is properly structured before further processing. This script shows how tuples can store a fixed, ordered set of clinical vital signs. It checks that the readings and their labels have the expected length, then prints the data and retrieves key values such as temperature, pulse, and oxygen saturation by position. By matching each reading with its label and verifying the tuple structure, The script demonstrates how tuples support reliable and efficient access to structured clinical data. Patient reading lists. A patient reading list organizes repeated measurements from one person in time order, making them more useful for clinical interpretation. A single value, such as one blood glucose reading, shows only a moment, but a sequence of readings can reveal whether a patient is improving or stabilizing. By preserving order and grouping similar values, lists help represent clinical records like temperature or blood pressure as a timeline of patient progress. Patient reading lists organize repeated measurements in the order they occur, helping show how a patient's condition changes over time. This can include vital signs during a shift, home blood pressure readings, or glucose checks across the day. Keeping the sequence intact gives each measurement context and supports the way medical data is commonly collected and reviewed. When building patient reading lists, keep each type of entry consistent so comparisons are meaningful. For example, use the same unit for body temperature and the same scale for pain scores. Extra details like time or device may be included, but related readings should stay in an ordered sequence. A well-structured list preserves both the data values and the clinical story they help tell. Python code patient reading lists. Lists help keep repeated patient readings in order, with each value representing an observation at a specific time. Using consistent units makes the readings easier and safer to compare. We create a list to store morning glucose readings in milligrams per deciliter. Each value is one observation, and keeping them in a list preserves their order so changes over time can be tracked. Temperature readings are stored in a list in the order they were recorded, using degrees Celsius throughout. Keeping the unit consistent makes later comparisons and calculations accurate and meaningful. To compare glucose changes over time, use the first reading as the earliest value and the last reading as the most recent value. Comparing these two values gives a simple view of how glucose levels have changed. A new glucose reading is added to the end of the list using the append method, which updates the list directly. Then the list length is checked to find the total number of readings, helping track observations for later analysis or reporting. To find the average glucose reading, add all recorded glucose values and divide the total by the number of readings. This gives a simple measure of the patient's typical glucose level across the recorded times. The output gives a quick summary of the recorded health data. It shows the full set of glucose readings, the first and most recent glucose values, the total number of measurements, and the average glucose level rounded to 1 decimal place. It also displays the temperature readings for a similar overview of that data. This script stores patient glucose and temperature readings, then summarizes the glucose data. It identifies the first and most recent glucose measurements, adds a new reading, counts the total readings, and calculates the average glucose level. It then prints a concise report with the first value, latest value, total count, rounded average, and the temperature readings. Patient data lookup. Updating patient records. Efficiently updating patient records means knowing how to find and change specific values in a collection. Since healthcare information can change often, collections let you update one field, such as a phone number, diagnosis, or emergency contact, without altering the rest of the record. This helps keep patient data accurate while preserving related details like allergies and visit notes. Choosing the right collection type is important when updating patient data. Dictionaries work well for labeled information that needs easy access and changes, such as blood type or insurance ID. Lists are useful when order matters, like tracking blood pressure over time, but require careful use of positions. Tuples are best for stable data that should not change, helping keep data management accurate and clear. Updating healthcare records must be accurate and purposeful, because each change can affect data integrity and patient safety. Clinicians need to distinguish between correcting existing information and adding new information, such as changing a temperature reading, adjusting a dosage, or recording a new medication. Data structures such as sets and dictionaries can help manage unique entries and connect related medication details, but the most important step is ensuring the correct patient record is updated. Python code: updating patient records. Use patient dictionaries to make updates easy to read, lists to keep patient observations in order, and sets to avoid duplicate allergy labels. A patient record can be stored in a compact dictionary that keeps related information together. In this example, it includes Jordan Lee's name, phone number, a set of allergies containing penicillin to avoid duplicates, and a list of blood pressure readings. This structure makes the patient's information easy to retrieve and update. The code first displays the patient's current phone number to confirm the record's initial state. It then shows the patient's allergies in sorted order, making the information consistent and easy to compare before any updates are made. This updates the patient record by changing the phone number stored under the phone entry. Assigning the new number directly modifies the existing record, so it contains the current contact information. A new blood pressure reading is added by placing it at the end of the patient's existing list of readings. Because Python lists keep items in order, this preserves the timeline of observations and makes it easy to track changes over time. A set is used to store patient allergy labels, so each allergy appears only once. When latex is added, the set keeps it as a unique entry. If penicillin is added again, it is ignored, because it is already present, preserving a clean list of allergies. A fixed visit date, June 11, 2026, is stored in a tuple containing the year, month, and day. Because tuples are immutable, this helps prevent accidental changes and supports data integrity when values should stay constant. The output confirms key updates in the patient record: the revised phone number, the most recent blood pressure reading, the sorted allergies list without duplicates, and the visit date stored in a fixed tuple format. The script updates a patient record by changing the phone number, adding a new blood pressure reading, and storing allergies without duplicates. It then displays the updated phone number, latest blood pressure, sorted allergies, and visit date. Dictionaries, lists, sets, and tuples are used to keep the patient data organized, ordered where needed, and free of repeated allergy entries. Patient key access. Patient key access means retrieving patient information by using meaningful field labels, such as patient ID or allergy status, rather than by remembering where the data appears in a record. In healthcare, this makes information easier and safer to find, such as checking whether a patient has a penicillin allergy. Labels also make records more readable, easier to maintain, and less likely to cause errors when new fields are added. Using keys to access patient data makes medical records easier to update and organize as care progresses. A key can point directly to information such as an address, medication, or treatment detail without affecting the rest of the record. This keeps related clinical information clearly labeled and helps staff retrieve or modify the right data within the workflow. When using patient key access, keep the data consistent, complete, and clearly labeled. Some fields may be empty because information is missing, pending, or not yet collected, so do not assume values are available. Using the same keys reliably supports accurate retrieval, summaries, and checks such as vaccination status, while reducing errors from memory or inconsistent labels. Python code, patient key access. Dictionaries let you access patient information by key. Each key retrieves a clinically meaningful value, and updates can change one specific named field. A patient record can be stored as a dictionary, where each string key points to a specific piece of patient information. In this example, the record includes a patient identifier, blood type, allergy information, and room assignment. This makes the data easy to access and update by using the appropriate keys. Retrieve the patient's ID and allergies from the patient record by using their corresponding dictionary keys. Then store those values for later use. Finally, print the patient's ID to confirm it was retrieved successfully. The code checks whether penicillin appears in the patient's allergy list. It uses a membership test that produces a true or false result, then prints whether the patient has a penicillin allergy. The patient's record is updated by changing the room entry to 14B. This modifies the existing dictionary value so it reflects the current room assignment, and the updated room number is then printed to confirm the change. A new entry is added to the patient record dictionary to store the latest glucose measurement with a value of 118 milligrams per deciliter. The program then retrieves and prints that entry to confirm the dictionary was updated correctly. Use the dictionary get method to safely read the patient record's follow-up information. By providing a default value such as not documented, the program avoids an error if that information is missing. The printed result will show either the recorded follow-up status or the default message. The process creates a concise patient summary by choosing only the needed fields: patient ID, room, and blood type. It uses those field names to pull the matching values from the full patient record and build a small dictionary. The result is then printed to show the selected patient information in an organized form. This script uses a dictionary to manage a patient record. It reads key details such as the patient ID and allergy status, updates information like the room number and glucose level, and safely handles missing data with a default follow-up value. It then prints a brief summary of selected fields, demonstrating dictionary access, checking, updating, and safe retrieval. List indexing. List indexing retrieves data by position in an ordered sequence, which is useful for patient information such as vital signs or glucose readings, where each position has a set meaning. Because indexing depends on stable order rather than labels, any missing or misplaced entry can return the wrong value. Maintaining the sequence accurately is therefore essential for reliable clinical interpretation and decision-making. Indexing lets you correct a specific item in an ordered list, such as one patient measurement, without changing the rest of the data. It is useful when order matters, like medication times or vital sign trends. Lists are best for repeated values of the same type, while mixed information, such as age and diagnosis, is usually clearer in key-based structures. Using list indexing for patient data requires accuracy and awareness of clinical context. Lists can store observations in sequence, which helps track trends and summarize a patient's care over time. Because healthcare workflows can be hectic, each list position must be checked to confirm what it represents, such as a time point or workflow stage. Careful indexing makes data management clearer and better aligned with clinical tasks. Python Code. List indexing. Practice using list positions to access ordered patient readings and update values when documented patient data needs correction. We create a list to store oxygen saturation readings in order. This makes it easy to track changes over time and access, update, or analyze the values for patient monitoring. The code first checks whether there are at least 4 oxygen saturation readings, so it can safely use the needed list positions. If enough readings are available, it stores the first and most recent values. If not, both values are marked as unavailable. The third oxygen saturation reading is corrected to 94. Updating that specific position keeps the patient data accurate while leaving the rest of the list in its original order. The append method adds the latest oxygen saturation reading, 97, to the end of the existing list, updating the patient's reassessment data. To work with specific oxygen saturation readings in Python, use zero-based indexing to get the third value with index 2. To get the most recent reading, use negative indexing with -1, which selects the last item in the list. These indexing methods help quickly access the data needed for analysis or reporting. The output gives a brief overview of the oxygen saturation data by showing the full set of readings, the first admission reading, the corrected third reading, the most recent reading, and the total number of recorded measurements. This script demonstrates basic list operations using oxygen saturation readings. It checks that enough readings are available, updates the third value from 93 to 94, adds a new reading of 97, and then prints a summary. The final output shows the updated readings, key selected values, and the total count. Collection methods. Append patient values. In clinical care, patient data often arrives over time, such as after nursing checks or lab results. Lists are useful because they keep entries in order and can grow as new information is added. For example, heart rate readings can start with one measurement and expand throughout a hospital stay, helping clinicians track changes over time. When adding new values, decide whether each entry should preserve history or replace what came before. Appending works well for records that grow over time, such as glucose readings or symptom reports, because older entries add context. But if the latest value should overwrite the old one, such as a room number or medication dose, use named fields instead of appending. When adding patient data, choose a structure that matches the clinical task. Lists work well for ordered records such as blood pressure, pain scores, or medication events with key details like name, dose, and time. Appending new entries keeps previous information available, making patient records easier to manage reliably. Python code. Append patient values. Lists can expand as new observations are added, while keeping earlier patient values intact. In this example, the list is used to track heart rate readings over time. A list is initialized with the first recorded heart rate, 88, representing the patient's admission value. Storing it in a list makes it easy to add later measurements while keeping the observations in order. New heart rate readings are added to the existing list in order: 92, 86, and 84. This keeps the patient's heart rate history updated chronologically for ongoing monitoring. To store detailed patient events, we can use a list of dictionaries. An empty symptom log holds each event, and each dictionary records key details such as the time and the symptom. For example, nausea at 8 o'clock. This makes patient symptom data easier to organize, manage, and retrieve. A new symptom event is added to the patient's symptom log, which stores each report as a dictionary. This entry records dizziness at 10:30, helping keep the log in chronological order so symptoms can be tracked over time. The program summarizes patient monitoring data by showing the heart rate timeline, identifying the latest heart rate, counting recorded symptom events, and displaying the most recent symptom entry with its time. Together, these outputs give a quick view of recent measurements and reported symptoms. This script shows how lists and dictionaries can manage patient information. Heart rate readings are stored in order as new measurements are added, while symptom events are recorded with their time and description. When run, the script reports the heart rate timeline, the latest heart rate, the number of symptom events, and the most recent symptom, making patient data easy to update and review. Updating collections. In medical data handling, choose the collection type based on how the information changes and is used. Lists work well for ordered, changeable data such as repeated readings. Dictionaries connect labels to values such as test names and results. And sets track unique items such as active diagnoses. Tuples are best for fixed information that should not be modified. In clinical data management, choose the data collection method based on the task. Use lists for ongoing ordered records, dictionaries for updating clearly labeled details, and lists or sets for removed issues depending on whether order matters. The right structure helps keep patient data clear, accurate, and less prone to errors. When updating medical data, protect data integrity, and make changes auditable because they can affect care and legal records. Simple corrections may replace old values, but clinically important changes, such as medication updates, often need a dated history. Choose the data structure based on what it represents, so patient information stays clear, safe, and meaningful as it changes. Python code, updating collections. Collections help make clinical updates safer by organizing patient information in structures that match the task. In this example, the focus is on choosing the right structure to update patient data clearly and reliably. Create a list to store Celsius temperature readings in the order they are recorded, making it easy to track changes over time. The list starts with 3 values, 37.1, 37.4, and 38.0 degrees. This structure also makes it simple to add, update, or remove readings later. To add a new Celsius temperature reading to a list, use the append method. It places the new value at the end, keeping the readings in order. In this case, the latest measurement is 37.8 degrees Celsius. The third temperature reading is corrected to 37.9 degrees Celsius. This keeps the temperature list accurate for later analysis or reporting. A dictionary can store vital sign measurements using clear labels for each value. For example, heart rate and systolic blood pressure are saved with their measurements, making it easy to find or update each vital sign by its label. This line updates the heart rate value in the Vitals dictionary to 84. It shows how dictionaries let you change specific information efficiently by using a key, which is useful for accurate clinical data management. This line adds the patient's oxygen saturation value, 97%, to the vital signs dictionary. It shows how a dictionary can be expanded with new measurements, so related patient data stays organized in one place. A set is used to store allergy labels such as penicillin and latex, ensuring each allergy appears only once. This is useful because sets automatically remove duplicates, keeping the allergy list distinct and easy to manage. This code updates a set of allergy labels, by adding iodine and removing latex. Using a set keeps the allergy list clean because each allergy can appear only once, avoiding duplicates automatically. A birth date can be stored as a tuple containing the year, month, and day. Because tuples are immutable, their values cannot be changed after they are set, which helps protect fixed information like a birth date from accidental modification. The code prints the updated contents of several data structures to show how each one behaves. It displays modified temperature readings in a list, changed vital signs in a dictionary, sorted allergies from a set, and an unchanged birth date in a tuple. Together, these examples show that lists keep order, dictionaries store key value pairs, sets keep only unique items, and tuples cannot be changed. This script shows how common Python collections can store and update patient data. Lists keep temperature readings in order and allow changes. Dictionaries store vital signs as key value pairs. Sets manage unique allergies, and tuples hold fixed information such as a birth date. The output displays the updated values while highlighting the main behavior of each collection type. Set methods. Sets are useful when you care about whether items are included and whether they are unique, not about their order. Unlike lists, sets do not keep a sequence, and unlike dictionaries, they do not connect items to values. They are well suited for distinct clinical items, such as unique allergies or diagnostic categories, because duplicates are handled automatically. Set methods are useful in clinical workflows because they handle unique items efficiently. A care coordinator can add new patient risk factors, remove resolved ones, and check what is present without creating duplicates. This makes sets a good choice for unique labels, unlike lists that may repeat entries or imply an order. Set methods help compare groups of distinct medical data items to find what they share, what differs, or who belongs in each group. They can support tasks such as medication reconciliation, screening tracking, and comparing infection control measures across hospital units. Sets are best for membership-based reasoning, not for ordered data or repeated measurements. Python code, set methods. Sets are useful for storing unique clinical labels. Their methods let you safely change membership, and comparisons help reveal how groups are related. We create a list of allergy labels that includes repeated entries, such as penicillin appearing more than once. This simple example shows why duplicate handling is important when managing clinical data. Convert the allergy list into a set to remove duplicate entries and keep only unique allergy names. Then display the results in sorted order, so the output is clear and organized. We add sulfa to the set of allergy labels, ensuring it appears only once because sets store unique items. Then we display the allergy list in alphabetical order to confirm the update clearly. To remove an allergy label that has been ruled out, use the discard method on the set of unique allergies. This safely removes the item if it exists and avoids an error if it does not. Then display the updated allergy set in sorted order to confirm the result. Two medication sets are used to compare a patient's treatment before admission and after discharge. The before admission set includes metformin, lisinopril, and atorvastatin, while the after discharge set includes metformin, apixaban, and atorvastatin. Representing the medications as sets makes it easy to identify what stayed the same and what changed. Medication changes can be identified by comparing the set of medicines before admission with the set after discharge. Medicines found in both sets were continued. Medicines only in the before admission set were stopped. and medicines only in the after-discharge set were started during the hospital stay. The code summarizes medication changes during a hospital stay by comparing medicines before admission with those after discharge. It shows which medicines continued, which were stopped, and which were newly started, using sorted results for clear output. This gives a quick overview of how the patient's medication list changed. To review a patient's medications, combine the medications from before admission and after discharge into one set of unique items. Then sort that combined set so it is easy to read, and print it as a complete overview of the medications considered during the stay. This script shows how set operations help manage clinical data by keeping entries unique and making comparisons simple. It removes duplicate allergy labels, updates the allergy record, and compares medication sets before admission and after discharge to find medicines that were continued, stopped, or newly started. It also combines the medication sets into one complete list, showing how sets can efficiently track changes in patient records. In this lecture, you learn to construct lists, tuples, sets, and dictionaries to represent common medical data items. Retrieve, update, and organize patient-related values using indexing keys and built-in methods. And choose an appropriate built-in collection based on the structure of a medical task. In the next lecture, Lecture B, we will go over text and files.
Thank you for your attention. See you all in the next lecture.